This is higher derivatives example number 6, and I've done some of the work already for us to kind of speed up the example, but we'll talk about what we did. Again, the key thing is we want to use our sum and difference rule. We're going to multiply, take the derivative of every term. So our inside thoughts here are, what is the derivative of x cubed? What is the derivative of y cubed? And what is the derivative of 5? And the derivative of x cubed, we know, is 3x squared, and that's what we start with. We start with the 3x squared. We know the derivative of y cubed is 3y squared, but then we have to take the derivative of our base function y. So that's why it's 3y squared with dy dx. And we know that if you take the derivative of 5, it's 0. And then we want to solve for dy dx. So we subtract 3x squared. It's like solving a two-step equation. Subtract 3x squared from both sides. Divide both sides by 3y squared. Divide both terms by 3. And our first derivative is negative x squared over y squared. We are supposed to find a second derivative. So looking at our first derivative, we have a quotient. So now our second derivative is going to be based on the quotient rule. So if I want to talk about my second derivative, if I use function notation f prime prime, I want to write this as a quotient rule. So my first derivative of f, or my derivative of f, is negative 2x. My g term in this case is y squared. I want to subtract my f value, but it's minus negative x squared. So I'm going to actually change that to plus x squared, and then times by my g prime. And my g prime is 2y, and I'm going to put dy dx here in red, because it kind of relates back to what we did farther up. And then my denominator is g squared. So if I look at what g was y squared. I want to square that. I want to know what my second derivative is without having reference to my first derivative. So we're going to use some substitution skills, and we're going to plug in what we know about dy dx. And when we found dy dx earlier, if we just scroll up a little bit, it was negative x squared over y squared. So like a lot of things you do in science and do in math, you replace expressions for equal values. So if I want to write my second derivative, negative 2xy squared is the very first part. I have 2xy squared for the second part. And then I'm going to add in my derivative, which is negative x squared over y squared. And we're going to clean this up in a second. And, oh, you know what? I have a mistake here. It's not 2xy squared. It's 2x squared y. Let's catch that before we get too far. 2x squared y in the top is we're multiplying all this together here. So that's what we're doing. And then the bottom hasn't changed. Well, we can simplify it. The bottom is y to the fourth. So let's just do a bunch of good math now and clean up what we have in the top of our fraction. Negative 2xy squared. If I multiply the green and the red together, I got x squared times x squared, a positive times a negative. I have negative 2x to the fourth. And if I have y divided by y squared, just to kind of keep things without fractions inside, let's go y to the negative 1. And the bottom is going to be y to the fourth. If you go back and think about some of our product rule questions, we said a lot of times the skills you want to have are your factoring skills. So let's look at what we can factor out of the top expression. And I see a negative 2 is in both those terms. I see an x is in both those terms. And when I look at the y squared and y to the negative 1, we're going to take the y to the negative 1 out. Exact same logic as to why we took just an x out. It's the negative 1 is smaller than negative 2, so you take the smallest one out. If you take the 2 away from the 2 and the x away from the x and then y to the negative 1 away from y squared, what's left in here is y cubed, y squared divided by y to the negative 1. Negative 2 divided by negative 2 makes our next term positive, and x to the fourth factor out an x makes this as x cubed, and y to the negative 1 take away y to the negative 1, the y value is out front, and my denominator is still y to the fourth. When you look at this, you're thinking, okay, let's just get rid of the exponent of y to the negative 1. So f prime prime of x equals, the 2 doesn't change signs, it's just negative 2 and it's x. And I'm going to put this in alphabetical order up here, x cubed plus y cubed, and I'm leaving it in blue for a reason. And when I move my y value from the top down to the bottom, it's like a 4 minus negative 1 or 4 plus 1. My denominator now becomes y to the fifth. What a great looking answer. And in fact, you think, well, Mr. Frank, we're done. But we're not done. If you went to the very start of our question, way up top, x cubed plus y cubed equals 5. We are actually going to use that information, x cubed plus y cubed equals 5. We're actually going to put that into the expression right up here where we have this set of brackets, because we can. And sometimes simplifying is just a practice thing, and this is one of those things where if you can substitute to make things simpler, we are going to substitute to make things simpler. So my second derivative is negative 2x. Instead of writing x cubed plus y cubed, I'm going to put 5 in here instead, and my denominator is still y to the fifth. So the best answer that we can have for our second derivative of this function is negative 10x over y to the fifth.